So in the last several segments, we covered selected topics in experiment design, hypothesis testing, and statistical estimation. And we motivated these topics by considering the so-called decline effect, where scientific results turn out to be less reproducible over time, or their effect size diminishes over time under repeated experiments. Okay, and we found that things like publication bias and the misapplication of statistical methods can explain a lot of this effect. Okay, and then we also talked about the Bayesian perspective, which allows you to incorporate prior knowledge easier, but opens the door to subjectivity leaking into the analysis, which is one of the reasons why it was largely rejected at the beginning of last century. But it's making a resurgence thanks to computational techniques that allow you to do sampling of complex distributions, at scale. And we didn't go into too much detail there, but I hope to get back to it before the end of the course. Okay. So in the next few segments, I want to talk about more of an algorithmic perspective that is more closely associated with the terms machine learning and data mining. Okay. So what is machine learning? So Pedro Domingo here at UW wrote a fantastic Communications of the ACM article in 2012 that gave an overview of machine learning. And what he said was that machine learning is systems that automatically learn programs from data. So what he means here is that when you write a program by hand, you're explicitly stating how to map a set of inputs to some desired output, right? You're giving a recipe for doing that. But the point is that given enough examples of inputs and desired outputs, you can infer the program that maps it as opposed to having to write it explicitly. So the joke is why bother writing programs when you can learn them instead? Okay. Maybe another view is teaching a computer about the world, but I perhaps prefer the first bullet here. Okay. So it's worth maybe a few minutes or just 1 minute or so talking about what the difference between statistics and machine learning is. It's probably not worth putting a lot of time into this or thought into this because, terms are not necessarily precise and they grew up in some historical context and reflect different cultures rather than being some well-defined notion that you can reason about. But there's a paper pretty long ago now, in 2001, that talked about a certain kind of difference, although they weren't specifically referring to machine learning. It captures what I believe to be the real salient difference here. Okay, and so the model here on the left is that everybody involved in the space is trying to do the following, which is, observe that nature is able to map inputs to outputs, and we want to be able to predict that, computationally. Okay. So the statisticians will attack this problem by, actually trying to model the world through some stochastic process. In the paper, they talk about data modeling. They talk about modeling the data. What they mean is modeling the process that gave rise to the data that you see. Okay, and so the idea is that once you have a model of the world, you can use it to sort of hypothetically draw more samples and reason about the entire population. Okay, but another view that's maybe this more algorithmic view is, look, we recognize that nature is difficult to model, and we don't really care if we have an accurate model of it. All we're trying to do is measure our performance in predicting the outputs that we've seen from given inputs. Okay, so it's not important that the model that we produce, that the program that we generate, actually reflects the real process that's going on in nature or not. We don't claim it does, but what we do claim is that it does a pretty good job making predictions anyway. Okay, and so I think this is the notion that's more associated with the machine learning approach. All right. So let me give you an example that comes from Witten that's used pretty ubiquitously to explain some of the concepts of machine learning. And we won't use this example too much, but it is useful for a variety of purposes. So imagine you're trying to predict when someone is going to play golf or play tennis or do some other outdoor activity. And we imagine that it's a function of the weather. And so we take in inputs like the outlook, whether it's sunny or overcast or rainy, the temperature, whether it's hot, cool, mild, the humidity, how windy it is, and we want to learn a function that takes in those inputs and produces a yes or no answer whether or not we play, say, golf. Okay, and so the simplest version of this you might do just intuitively is just try to predict it with a simple rule. So you might say, look, maybe we only play when it's sunny. Is this true or not? Well, no, it's not true because we can find examples where we did indeed play when it was overcast. Okay, you might say, well, maybe we don't play if it's rainy and windy, and that turns out to be true, but there's also other times that we don't play as well. So the pattern that, if a function exists that can predict this output well, it's perhaps not something that we can express in just one simple rule, which is kind of the limit of what we can do, mentally just through intuition. And so the idea is we need some principled way of coming up with more complex models when they're needed. Okay. So fine. So some terminology. This problem is an example of a classification problem where there's a learned attribute and it's categorical. It can take two values in this case, 0 or 1. If the learned attribute is more of a numeric value, for example, what our score at golf was, as a function of the weather, if we want to try to predict that, that would be more of a regression case. Okay. And really not just learned attributes, probably when all the attributes are numeric, it becomes more of a classical regression case, although there's ways to handle this. And so we've talked about regression in terms of, fitting a curve to data, but when you use that fit curve to actually make predictions, that's when it's you can see that it's analogous to the classification problem over categorical data. Okay. So more terminology. The golf example we just gave is an example of supervised learning, where you're given examples of inputs and the desired outputs, and we're trying to learn the relationship between them. So we train a model to do this. And there's also a notion of unsupervised learning, which is you're not given any labels whatsoever. You're just given the data, and you're trying to understand the underlying structure in that data. Okay. So this is things like clustering algorithms or dimension reduction algorithms, if you've heard those terms before. So let me give you an example that can be sort of cast as either supervised learning or unsupervised learning, but it's instructive as an unsupervised learning case for right now. So imagine you're just given a big corpus of documents, and you're trying to figure out, you want to make a prediction of what topic a given document pertains to. And so, if you see the phrase, the Falcons trounced the Saints on Sunday, you might guess that this document is about sports, while if you see that the Mars rover discovered organic molecules on Sunday, you might guess that this document is about science. And so, how do you set this problem up as a machine learning problem? What are the rows and columns? We just had an example where there's sort of rows and columns, and we said for one record, we're trying to predict the output given the inputs. What are the rows and columns here? Well, this shouldn't be too bad since you've seen this before in a couple of assignments now.